We're here to explain to you all today related rates. Now, a lot of what we do with related rates deals with rates of change, and you probably already know what a rate of change is, but in case you forgot, I have an example. My Calc grade senior year had a rate of change of about -5% per quarter, which means that my grade went down by an average of 5% each quarter throughout the year, which is why I'm completely qualified to explain this concept to you. Related rates gets a little more complicated than the rate of change problems that you might be used to.
With related rates problems, we're usually trying to find a rate of change of a particular quantity of a figure when other rates or quantities are given. For example, if we know the rate at which water leaves a cylinder, like this water bottle, we can use related rates to find the rate at which the height of the water in the bottle decreases. Okay, so we're going to first start with showing you how to do a 2D figure. So I'm going to write a sample problem and then we're going to work through it step by step. The radius of a circle is increasing by 1 inch per second. When the radius is exactly 4 inches, what is the rate of change of the circle's area? So when we have a problem like this, we're first going to start off by identifying what the problem gives us. So we have a few rates of change that they give us. So we know that the radius of the circle is increasing by 1 inch per second. That means that dr dt, because it's always going to be over time, dr dt is 1 inch per second, and it's going to be positive because it's increasing. We want to find what the rate of change is when the radius is 4. So our r is going to be 4 inches. So we know that, and we are trying to find the rate of change in the circle's area. That's going to be dA dt. It's always in respect to time again, but that is our unknown. So when we have a problem like this, we're first going to have to know what the area of the circle is. So the area of a circle is pi times the radius squared. We're trying to find dA dt. So what we can do is we can find the derivative of our area equation of the circle. So it's going to be dA dt equals, you're going to find the derivative, so you're going to take the power rule, do 2 pi r, and then you're going to make sure to also take the derivative of r, which is again in respect to t, so it's going to be dr dt. So now we have this equation for dA dt. We have a value for dr dt, so we can plug that into that, and we have a value for r, so we can plug that into that. So then it's going to be dA dt equals 2 pi times r, which is 4 for us, 4 inches, times dr dt, which is 1 inch per second. So then when we simplify that, we get 2 times 4 is 8, times 1 is 8. So it's going to be 8 pi inches squared per second. And that's going to be dA dt when r equals 4 inches.
Next, let's do a three-dimensional example.
A tank of water shaped like a cone is leaking water at a rate of 2 feet cubed per hour. When full, the radius of the cone is 5 feet and the height is 10 feet. At what rate is the height changing when it is 6 feet?
So let's first draw a picture of what's going on here. So we have a cone. I'm a great artist. And when it's full, the radius is 5 feet and the height is 10 feet. And then at some other radius, which we don't know, the height is 6 feet. And this is the value that we're going to be dealing with because that's where we want to find the rate of change of the height. So let's look at what we're given in this problem. We know that dV dt, or the rate of change of the volume, is negative 2 feet cubed per hour. And the reason we know it's negative is because it's decreasing, not increasing. And then we know that the height at the point we're solving for is 6 feet. We don't know the radius at that point. And because we don't know the radius, we need to find r in terms of h because that's going to make things easier later on. So how we do that is we do 10 over 5 equals h over r because we know that when the height is 10, the radius is 5. And then when we cross multiply, we can find out that r is 1/2 h. So now let's take a look at the equation for the volume of a cone. It's V equals 1/3 pi r cubed h. And what we're going to first do is we're going to switch this r to get it in terms of h, since we don't know what the r is at the point. So we're going to replace it with what we found over here, 1/2 h. And now we're just going to simplify this. So remember, our fully simplified equation for v is 1/12 pi times h cubed. And now we can take the derivative of this. So dv dt, since we're doing all this in terms of time, is going to be 3 times 1/12, which is 1/4, pi times h squared. And of course we have to have dh dt since we're doing this in terms of t. So now we can start plugging in the values that we do know. So we know that dv dt is -2 feet cubed per hour because we were given that. And then we know that the height at that point is 6 feet. And of course we don't know what dh dt is because that's what we're solving for. So now all we can do is simplify and try to get dh dt by itself. So after I did all the simplifying that I could, I got that -2 over 9 pi feet per hour is the rate of change of the height, and that's approximately -0.071 feet per hour. So that's going to be our rate of change for the height.
Okay, so now we're going to do a falling ladder example.
A ladder is slipping away from a wall. The distance from the bottom of the ladder to the wall is increasing at 2 feet per second. Find the rate of change of the distance from the top of the ladder to the ground at the time where the ladder is 10 feet from the wall.
So we're going to draw a picture for the problem. So start off, right triangle. We're going to call this one side A, here's side B, and then side C. C is 15, and that's not going to change because the length of the ladder won't change during the problem. Here on side A, this is the side that's going to be moving away from the wall. So we're trying to find the dBdt when A is 10 feet. And in the problem we gave that the dAdt is 2 feet per second. Alright, so we're going to start off with the Pythagorean theorem for a right triangle. So a squared plus b squared equals c squared, and we already gave you c, which was 15, so c squared is 225. Then we're going to take the derivative, so we have 2a dAdt plus 2b dBdt equals 0. We're going to plug in what we know, so we know that a is 10, dAdt is 2, and then we don't know dBdt or b. Okay, so to find b, we can just use this formula and then just solve for b. So b squared equals 225 minus a squared, and we already know a as well, so that would just be b squared equals 225 minus 100. So b equals the square root of 125. So then plugging that in, 2 times 10 times 2 plus 2 square root of 125 dBdt equals 0. And then plugging that into your calculator, you get dBdt equals -1.789 feet per second.
Now let's do a couple practice problems. Here's the first one. The volume of a sucker being licked is decreasing at a rate of 1 millimeter cubed per second. Find the rate at which the radius is changing when the radius is equal to 5 millimeters. And here's the second one. The bottom of a 13-foot ladder is being pushed towards the wall that it is leaning against at a rate of 1 foot per second. When the base of the ladder is 5 feet away from the wall, at what rate is the height of the top of the ladder changing?